Welcome back to Wood Engineering. I'm Jeff Roachko from Carleton University, and in this video we're going to finish up this tension design example that we looked at in the previous video, but this time we're going to design the member for Glulam. So previously, when we looked at this design for tension, we found all of the different load combinations that were possible for those three loads on the member. Then we determined which one was going to govern, which we happen to be able to do because this is tension design, but we can't always do. This wouldn't work for compression design. For compression design, I have to do 3 different calculations for resistance, 1 for each different KD, and then compare all 3 separately, which is quite a long process, but unfortunately necessary because in compression parallel resistance, the resistance is not linearly proportional to KD, but for tension it is. So for tension, we can actually just divide TF by KD to see which one governs. And in this case, we found that we had a KD that governed of 0.849 combined with the load case of TF equals 200. So basically these become our design criteria. And then we went through for lumber, and for KD of 0.849 and TF of 200, we used the design tables to pick a design member, taking into account all of the different reductions that are not in those design tables. And then once we did that, we checked to make sure that the member that we designed actually satisfied all of our criteria, including ST, and KT. One thing that I didn't mention before, because we see here that KZT, the size factor, is not equal to 1. That size factor is taken into account in the table resistances. So obviously, because different size members have different resistances because of the size effect factor, in the tables of resistances in the wood manual, KZT is included. So those member resistances include consideration of KZ. Okay, and we came up with tension design for lumber, and it was a 241 by 241 member, which was basically the biggest one. Okay, so now we're going to repeat the same process for Glulam, and we're going to recall again the TF is 200 kilonewtons, and that is coupled with a KD of 0.849. So whenever I have a TF, it's not defined on its own. That TF is associated with a certain KD. So in this case, the TF was from a load combination that included dead plus live only. For that one, since dead was greater than live, we used the interpolation equation to get KD, and that ended up with 0.849. Okay, so now we're going to go through the same process, but I'm going to include a new concept which was not included before, and that is that for Glulam, in most cases, we always have to do this check of net section strength and also gross section strength. So you recall that for Glulam we have 2 TR equations, and it depends, whichever one governs, like whichever one has a lower strength is the one that we're going to use. But it turns out, and it says this actually in the design manual, it turns out when it talks about Glulam in this section on tension members, and this is the case because of how these TR and these TRG and the FTN, and FTE values are defined, the strengths for tension, for net and gross, is that you'll see here the resistance in the paragraph just below the numbers. The resistance at gross section will always govern the design of a member as long as the net area is no less than 0.78 of the gross area for 18 TE Glulam and 0.75 of the gross area for 14 T, 20 FEX, and 24 EX Glulam. Okay, and then it reminds you that the minimum permitted net area is 75%. Remember, we can only cut out 25%. So it's saying here that for almost every case, the gross section resistance will govern the design. But on the tests and stuff, check both, because it pays to just be consistent and make sure that we don't end up in that area where we're just a little bit less, we're less than 0.78, and we happen to use 18 TE Glulam, which could come up. So just make sure you check both. But the consequence of this is that when we go to the design tables, we can basically assume that everything is failing in tension gross and use only those parameters to figure out what my target should be. So you remember before when we did lumber, you know, I said we have a target F. We're looking for a resistance here greater than 200 divided by the KD of, which gave us 235. But then when we got to actually looking at the design tables, I remember that we forgot to include the fact that we have to reduce our area for net. So we had to go basically one section bigger. So we won't have to consider that affecting Glulam because the gross is typically going to govern. Okay, so we know that we're going to use Douglas fir larch 20FEX. Okay, so that was given in a design problem. So now let's go to the table. We're going to go to the tables in a minute and figure out what our actual strength should be. But before we do that, let's figure out what our KH is going to be 1.0 because we have one member by itself, so there's no sharing of load. KST we don't know, and KT we don't know. So let's go to those tables, because depending on what KST and KT are, we might need to modify our expectations for what we look at in the design tables. So here is the service condition factor for Glulam. So I have KST, tension parallel to grain. It only has a difference between dry and wet. And you'll recall that for this problem, our service condition is wet. So we're going to have to use basically this value here, 0.75. Okay, so that's our KST. And for KT, for KT for Glulam, it states in the code that basically it's always going to be 1.0. So let's go back. So KST is going to be 0.75 and KT is going to be 1.0. All right, so then if we want to get a target strength, so this is our TR target. From the table, we can take our TF basically, and this is what we did before, we can divide by KD, by KH, by KST, and by KT. And if we do that, we're going to get a target of 314 kilonewtons, okay, where KD is 0.849, KST is 0.75, and KT is 1. And if I was doing something with net area, then I would also divide by, you know, how much my net area is reduced compared to my gross area. But as I said, we're going to look at only gross value properties for the table. Okay, so our target force here is 314 kilonewtons. So now I can go to the design tables in tension, and this is just below where we were. So here we were before for sawn timber when we were trying to find a lumber size. So if I just scroll down, I have this table, which is for these two grades of Glulam, 18T and 14TE. Now we actually are dealing with 20FEX grade, so I need to go to this table, and you see there's only one table here for Glulam. Okay, so that's the end, basically, of this section. Okay, and remember my factored resistance target was 314, so I can just read down the list here. You see, so here's one option is 335, which is greater than 314, and that's an 80 by 304. Here we have another option if we come down, 340, which is greater than 314, which is a 130 by 190. So this is really a design decision, which one of these I would like to go with. One that's kind of more rectangular or one that's more square. Since it's a tension member, maybe it makes more sense to take the squarish one because it is, it's going to look more compact, and I don't need the extra depth for bending. If I had a big connection that I need to design for this, which maybe I might, then maybe it would be a good idea to go with the deeper one. But anyway, so let's go with this one for now, 130 by 190. So I'm going to go back to our calculation and say we are going to choose select D for larch 20F EX 130 by 190, and then I'm just going to go through and check that this works. Okay, so first let's find the design strengths for that. So for that, I'm going to go to the strength table. For Glulam, okay, so this is the Douglas fir larch part. The next part is spruce pine. So Douglas fir larch, 20 FEX, and I'm looking here for two different strengths. One is my gross section strength, and one is my net section strength. So I have two, FTN of 20.4 and an FTG of 15.3. So those are the two different values that I need to use for the two different strengths. Okay, so FTN was 20.4 MPa and FTG was 15.3 MPa, and my gross area is 130 times 190, which equals 24,700 millimeters squared. And my net area, which we're assuming to be 85% of the gross, this is not always the case, this is just an assumption that we made in this case, is going to be 2995 millimeters squared. Okay, so now I can figure out FTN, capital FTN, and capital FTG, and we'll remember this is small FTN times KD times KH times KST times KT. And this is going to equal 13 MPa in this case. The only reduction that I have basically is my KST of 75%. And this is FTG, KD, KH, KST, KT. You're going to know that off by heart. KD, KH, KS, KT. And we get 9.7 MPa. And now I can do the tension resistance equation, which is phi FTN times AN. That's the first one. So this was TR1. And if I do that, and phi is 0.9, if you'll recall, then I get a strength of, so this is 0.9, FTN is 13, AN was 2995. I'm going to get 245,600. This is in newtons, so I get 245.6 kilonewtons. And if I do my second one, which is for gross area, T gross times AG, 0.9 times 9.7 times 24,700, I get 216.7 kilonewtons. So you can see, just like the design manual said, for this case, since my gross area is greater than 75% of my net area, then it's the TR2, the one that uses gross area, that governs the strength. This is the lower one, so that's my actual strength. So therefore, TR is 216.7 kilonewtons. So now recall that my TF, right, just like before, my TF is 200 kilonewtons. And therefore TR greater than equal to TF. So I'm good to go. Okay, so my design is a Douglas fir larch 20F EX grade 130 by 190. And now I've gone through the entire design process, starting at load calculations, picking a section out of the table, and then coming up with a final check on my strength and my final design. And then, of course, I mean, there's nothing really to draw here because it's just one member, but if I had connection or if I had multiple members, now I can put these in my drawings.